Well, welcome back, everyone. So what have we done so far? Well, last series of lectures, we talked about one type of an outcome measure, namely prevalence. And more recently, this time, we've been talking about a different outcome measure, namely incidence. But let's go back to the previous series of lectures, prevalence. And at that point, we made a point to talk about what sort of factors influence the value for a prevalence. Well, first of all, remember prevalence is a proportion, the proportion of people who have some characteristic, like a disease, at one point in time. And we've been using the Framingham data set to look at such things like the prevalence of coronary heart disease among people at their 1956 examination. And you've been using that in your STATA exercises. Well, what determines how high a prevalence is? Well, one thing I said, it depends on how quickly people develop the disease. If you come across a population with lots of diseased people at some point in time, it may reflect that that's a high-risk population. People are constantly developing disease in that population. So when you came along with your camera and took a snapshot, a prevalence measure at one point in time, you're seeing a high value for the prevalence because it's a high-risk population. I also said prevalence also depends on another measure, namely the duration of disease. Maybe the reason that you see a high prevalence in a certain population is because that population is not at a typically high risk for developing disease, but people who develop disease in that population live for a long time with their disease. Their duration is long. So the important message I was trying to stress at that time is that prevalence is a function of two measures, incidence and duration of disease. Well, that's the concept I was trying to raise at that time. Right now, I'd like to give a more formal relationship, a mathematical relationship that holds in a very special case where you can actually determine the prevalence by knowing the incidence and the duration. But up front, I want to say this is a somewhat hypothetical special case. You might not run into it in real practice. The important message is to remember that prevalence is a function of both incidence and duration of disease, rather than to worry about this special case. But let's go through the special case to derive a mathematical relationship between the prevalence of disease in a population and its incidence for developing disease in that population and the duration of disease in that population. And to describe it, I'm going to use the following figure. I'm going to describe what is known as a steady state, a population that doesn't change over time, a population that's not getting bigger or not getting smaller. At any point in time, there are the same numbers of people living in that population. Maybe some of the people's characteristics might have changed over time, but at any one point in time, there might be 10,000 people living in this population. Now, that population is made up of two types of people, people with the disease and people without the disease. And I'm going to make the added assumption that those two subpopulations, their size don't change in time. But remember, as people grow older, as you follow people over time, some people develop disease. And if this is a disease that's curable, then some of the people who have the disease over time will become cured from the disease. So what you're going to have in this steady state situation is movement between these two subpopulations. Some of the people in the top of this box, the disease portion of the box, are going to be cured, and they're going to move down into the other part of the box, which is made up of the non-diseased people. And they're going to be balanced off by movement in the opposite direction. People who don't have the disease are going to be developing disease. And for these two subpopulations to stay in the same size, the same steady state, essentially the numbers of people moving down, being cured of their disease, has to be balanced by the number of people moving up, developing disease. Well, what describes the movement? And what describes the numbers of people who are moving down or moving up? Well, in terms of the diseased people, if I say every point in time I have the same numbers of diseased people, and I have n people at any point in time in the entire population, the number of diseased people is going to be nothing more than n times the prevalence. If I have 10,000 people in a population, and the prevalence of disease is 10%, then 10% times 10,000 people, 1,000 people will have the disease, and 9,000 people won't have the disease. So what's the number of people who don't have the disease in this population at any one point in time? It's that same n being multiplied by 1 minus the prevalence. Well, those are the steady numbers in this steady state of disease and non-diseased people. And if I say there's movement from the disease group being cured and movement from the non-disease group being developing disease, and they're being balanced out, then I have to take into account the force that's driving people to develop the disease and the force that's driving people to be cured of the disease. And those forces are what we referred to as incidence rates before. These two arrows are describing the movement, the forces that describe the development of disease among the non-diseased people and the development of cure among the diseased people. So the bottom arrow here, which I label incidence rates, is describing how many cases of disease occur in a population that's being followed over time. That's what we've been talking about in the more recent series of lectures. That's going to be balanced by another incidence rate. We'll call it the cure rate, the number of cases that are cured when a population of diseased people is being followed over time. And now to mathematically stay in this state of equilibrium, in this state of steady state, the numbers of people multiplied by the force that's driving them to be cured has to equal the number of non-diseased people multiplied by the force that's driving them to develop the disease. We can write down an equation that says the number of people with the disease, n times the prevalence, times the cure rate. That's describing how many people are moving down from the top part of this box to the bottom part of this box. To remain in a steady state have to be equal to, balanced by, the number of people moving in the opposite direction, which is the number of non-diseased people, n times the 1 minus the prevalence, times the force in the other direction, which is the incidence rate. So that's the starting point of this relationship between incidence and prevalence. Let me rewrite that bottom equation on the top of the next line. So here's what that equation says. N times the prevalence times the cure rate is equal to n times 1 minus the prevalence times the incidence rate. We can simplify this a little bit. We can cancel out the n's in both sides of the equation. They cancel out. I can divide both sides of the equation by 1 minus the prevalence. Bring it on to the other side of the equation. And what I will have when I do that is an equation that says prevalence divided by 1 minus prevalence equals incidence rate times divided by the cure rate. What I'm going to do is I'm going to take the cure rate and put that on the other side of the equation. Well, the left-hand side of this equation is something that we've seen before. A prevalence is a proportion, the proportion of people with disease. Prevalence over 1 minus prevalence is the odds of having disease. So this equation can be simplified by saying that the prevalence over 1 minus prevalence, or the odds of having disease, is equal to the incidence rate divided by the cure rate. Well, let's think about that cure rate for a minute. Let's suppose I have 10 people with disease, and I follow them for 10 days. I observe 100 person days of people who are sick having that disease. And let's suppose out of that 100 person days of following them over time, that 5 people become cured. What's the average duration of disease? How long does a person stay with disease? Well, it's going to be the inverse of that cure rate. So the cure rate is going to be nothing more than 1 over the average duration of disease, and let's represent that by 1 over d. So now what do I have? I have the prevalence over 1 minus prevalence is equal to the incidence rate divided by 1 over the average duration of disease. Well, if you have divide by 1 over the average duration of disease, that's the same thing as multiplying by the duration of disease. So now we have the formula that describes the relationship between incidence, duration, and prevalence for the steady state. It says your prevalence odds, your prevalence over 1 minus prevalence, is equal to the incidence rate times the average duration of disease, which jives perfectly with what we had conceptually said before. High prevalence in a population can be caused by or attributed to either that population having a high incidence or having that population have a long duration of disease. So this formula, prevalence odds equals incidence times duration, is a mathematical expression of the relationship between incidence, duration, and prevalence in this steady state. One last comment to make. Remember we talked about odds before. And I said for a small proportion, the value for the odds corresponding to that proportion is almost the same number. If the proportion or the prevalence of disease is 1%, the odds of disease is 1% divided by 99%, which to 2 decimal places is still 1%. So if you have a small prevalence, say less than 10%, this general formula that says prevalence odds is equal to incidence time duration can be re-expressed more simply by saying prevalence itself is approximately equal to incidence times duration. And this is the one you might see more oftenly cited in introductory epidemiology books to describe the relationship between incidence and duration and prevalence. The formula is nice. I bet you're not going to run into many steady states in your life where you can apply this mathematically. The important thing is it underscores the relationship between prevalence, incidence, and duration. And that's the important thing I want you to remember. If you have a high prevalence of disease in a certain population, it might be due to the fact that that population is at high risk of getting disease, or it might be due to that population have long durations of disease. And if you're interested in identifying risk factors for causing disease, if you're interested in incidence, that means that prevalence data is not going to be very useful. Because if you're using prevalence data and you find a subgroup of people, say smokers, with higher prevalence of disease than non-smokers, you'd like to say smoking is causing disease, but you can't. You don't know whether the relationship is due that smoking somehow extends the duration of disease compared to non-smoking. And that's the problems of prevalence data. Next thing I want you to do is some problems using prevalence data. I'll give you the problems and show you the solutions. See you next time.